Then of course this expression here would expand. Yeah? If we have 3 restrictions, for instance, so then we would have this guy here would be 1 by 3, this guy would be 3 by 3, this guy would be 3 by 1, and again what would come out is a random number that is then distributed under the null hypothesis with 3 degrees of freedom. Okay? So now we can wonder, okay, why do we need to do that? Why do we need this kind of test statistic? So if we have if we just are interested in testing a single parameter here, then we can just have a look on the t statistic. Yeah? So, and we have already talked about how it looks like. Yeah? We grab the corresponding element from the parameter vector and divide it by the square root of the corresponding element of the main diagonal of the covariance matrix from our beta hat vector. Okay, simple, very simple. But if we are interested in testing more than one parameter, in this case 2 parameters jointly, then we have to take into account the covariance between those parameters. Because obviously this has an impact here on how the test statistic looks like. Okay, so having defined this, I have to take this away now because we need some space. We can do it we can do it once so that you understand, that you see basically in detail how it looks like. So we have defined our R and we have defined our covariance matrix. So again, this guy here in the middle, that's a 4 by 4 matrix. Yeah. Let's take the black pen. So we have the sigma square 1, which is the variance of the alpha, because that's the first element on the main diagonal. Then we have here the sigma 1, 2, which is the covariance between the alpha and the beta 1. We have the sigma 1, 3 and sigma 1, 4. Yeah? Sigma 1, 4 is obviously the covariance between the alpha and the beta 3. Yeah. So, and so on. So we can basically just write it down here in the same manner. So we have on the main diagonal the corresponding variances 1, 2, 3, 4. The corresponding variances in line with our 4 parameter estimates, and below and above the main diagonal we have the corresponding covariances. So here we have the sigma 2, 1, yeah. Here we have the sigma 3, 1 and sigma 4, 1. Here we have the sigma 3, 2. Here we have sigma 3, 4. Yeah. Here on the main diagonal for the second parameter, it starts with sigma 2, 1, sigma 2 squared. Then we have sigma 2, 3, sigma 2, 4. Last row, it starts with sigma 4, 1, yeah, which is the covariance between our fourth parameter with beta hat 3 and the alpha. Yeah. Then we have sigma 4, 2, which is the covariance between the beta hat 3 and beta hat 1. Then we have the sigma 4, 3. And then finally we have here the variance of our beta hat 3, which is here in our covariance matrix, the sigma 4 squared. Yeah, so we recognize here on the main diagonal they are the squared. These elements are squared because these correspond to the variances of each of these parameters. Yeah. So in here, in this expression here in the middle, we multiply this covariance matrix with R. Yeah, and we have defined R already. So this is a 4 by 4 Yeah, this is 4 by 4, and our R looks like this. So we have our 0, 0, 1, 0, and our 0, 0, 0, 1. Yeah, that's our R. So if we multiply this out, what comes out here is obviously, so first we have to multiply this row with each column. So if you multiply this row with the first column, we get the sigma 3, 1, which is the covariance between the third and the first point estimator. If we multiply this row with the second column, we get sigma 3, 1. So we get basically the whole third row. Yeah? And we put it here. So sigma 3, 1, sigma 3, 2, sigma 3 squared, and sigma 3, 4. Next, if we multiply the second row of our R with our covariance matrix, it basically depicts us the last row here, and we put it here. So what we get here is our sigma 4, 1, sigma 4, 2, sigma 4, 3, and finally our sigma 4 squared. Yeah? Let's write this down here, because now we have to multiply this guy here with our R transposed. So how does this look like? So let's just write it down here. Let's just copy that. Sigma 3, 1, sigma 3, 2, sigma 3 squared, and sigma 3, 4. And then the second row we have sigma 4, 1, sigma 4, 2, sigma 4, 3, and sigma 4 squared. And we multiply this now with our R transposed. Yeah? So we have to transpose this guy, and then it becomes obviously a 4 by 2 matrix. Yeah? The first column 0, 0, 1, 0, which is the first row here, it becomes a column vector, and the second row vector becomes a column vector of 0, 0, 0, 1. So now we note this matrix here, what we have here, is obviously 2 by 4. This is a 2 by 4 matrix, and we multiply it with something that has a dimension 4 by 2. So what comes out, as we said earlier, it's a 2 by 2 matrix. Yeah? And how does it look like? Well, if we multiply the first row with this column vector here, what it gives us is this element sigma 3 squared. So we have the sigma 3 squared as our first element here. Next we have to multiply this row with the second column vector, and what it gives us is sigma 3, 4, which is the covariance between this guy and this guy. Yeah? Yeah? This guy here times this vector here gives us the sigma 3, 4. Then next we multiply again. We multiply the first row, the second row with the first column vector, and what it gives us is the sigma 4, 3. Yeah? Sigma 4, 3, which is the covariance between the fourth and the third parameter, yeah? Between this guy here. And obviously these guys here these are the same numbers, because the covariance between the third and the fourth parameter is the same as the covariance between the fourth and the third parameter. Next we multiply this second row with the second column here, and what it gives us is the last element, obviously. Yeah? So it's the sigma 4 squared, which is the variance of our fourth parameter in the parameter vector, which corresponds to our beta hat 3. Yeah? So obviously in this formula here, this expression here, yeah, is then inverted. Yeah? So we have to invert, we have to take it times to the power of -1. Yeah? So we have to invert this matrix here. But once again, what gives us this matrix, and this is what I told you earlier already, so this expression here, it depicts the corresponding variance and covariances of the point estimator. So we have here on the main diagonal, we have the corresponding variance of these parameter that we are interested to test. The second element is the variance of the second parameter that we are interested to test. And above and below the main diagonal, we have the covariance between those parameters. Yeah? So this is what it does. Yeah? And what do we have here? Yeah? On the right and on the left, we have obviously, it gives us, if we multiply our R, our parameter vector, yeah, it gives us the corresponding parameters that we are interested to test. So R times our beta hat vector gives us the beta hat 2 and the beta hat 3. Yeah? This is R times beta hat. Minus R, which is this vector of 2 by 1 vector of zeros, doesn't change anything. So this is basically what we have here. We have to transpose this guy. If we multiply it from the left, we have to multiply it. So this becomes then a row vector, which looks like this: beta hat 2, beta hat 3, times this guy here, inverted, times this guy here, which is beta hat 2, beta hat 3. This is this guy here, was on the right hand side. So, and if you multiply it out, what we get is obviously 1 by 2 vector times this guy here, 2 by 2 matrix inverted, times 2 by 1. What we get is a number. And this is a random number. It's drawn from the chi-square distribution with 2 degrees of freedom under the null hypothesis. Whatever is this number, we have to compare it obviously with the critical value of the chi-square distribution with 2 degrees of freedom. Let's take this away now. So now we have seen basically how it looks like if we multiply it out. Luckily we don't have to do it. Obviously our matrix program, our MATLAB program, will do the job for us. We just have to define the matrices, we plug in the formula, and our program will provide us with the corresponding estimates. So what about the chi-square distribution? So we have again, as opposed to the normal distribution, the chi-square distribution with 2 degrees of freedom is obviously, it looks like this. It has only positive values, and if we have 95% probability, here's 95% probability, 95, the corresponding critical value is obviously 5.992. So again, under the null hypothesis, these two guys here are 0, and it would imply in our framework here that the cap M, or that the cap M is the right model, because obviously if our null hypothesis holds, the Farman-French, the additional risk factors from the Farman-French 3-factor model do not add anything, because the parameters are 0. So whatever comes out here, if the corresponding value of the test statistic is larger than 5.992, then we would reject the null hypothesis, because then obviously those guys here are jointly significantly different from 0. So if we reject the null hypothesis, then obviously adding the Farman-French size and value factor to the market factor adds value. Whereas if the corresponding estimated test statistic, if the value is below 5.992, then given we have a 5% significance level, we would not reject the null hypothesis. So in this case, we would assume that those parameters here are jointly not different from 0, and obviously the two additional risk factors of the Farman-French 3-factor model then would not add anything, and the model under the null hypothesis, which is just the cap M model, would be then the correct specified model. So this is basically what we were talking about also in the RFM course, That's basically what in the Farmer and French 2018 paper is referred to as test for nested models. Yeah? So you remember what they were doing basically when they were testing the 6-factor model, yeah, against the 5-factor model. What they were doing basically, they had here on the left hand side the momentum factor, yeah, and they were regressing the momentum factor on the risk factors of the 5-factor model. Yeah? And then they were testing if the alpha would be significant. Yeah? They were testing if the alpha was significant. Yeah? So the R obviously looked different. So in this case, you could actually just use a simple t statistic. Yeah? But you could also, of course, use our Wald test, obviously. So in this case, the Wald test would be distributed as a chi-square distribution with 1 degree of freedom. Yeah? Because then if you have just one restriction or one condition here, then we have obviously the test statistic becomes a chi-square distribution under null hypothesis with 1 degree of freedom. Yeah? And the critical value would be then something like 3.84. Yeah? So that's the Wald test, and the Wald test can become quite fancy, I would say, because you have to run the model under the alternative hypothesis. Yeah? So the Lagrange multiplier test has the same distribution under the null hypothesis. Yeah? So if we would test this model here using the LM test, we would have a different approach. Yeah? We would estimate the model first under the null hypothesis and not under the alternative hypothesis. Yeah? It's a different approach, but the corresponding reference distribution under the null hypothesis is the same. Chi-square distributed with 2